This is example 15.1 from Discovering Design with Chemistry, and now we are in the chapter about kinetics. So the reaction below is first order with respect to H2 and second order with respect to NO when the concentration of H2 is 0.012 molarity and the concentration of NO is 0.045 m. The rate of the reaction is 3.41 m per s at 25 degrees Celsius. What is the rate constant and overall order for this reaction? So let's start with the rate constant because that one's easy. They told us that it was first order with respect to H2, so we're going to use X for that. That means 1. And then with respect to NO, it told us it was second order, so we're going to call that one Y. For the rate, the overall order for this reaction is just add those two numbers. That's 3. The rate constant, however, we have to do a little bit more work for. The rate constant is this K right here in this new equation we've just learned. So we have to label the stuff that we found so we can plug it in. So they've given us because I labeled X as 1 because I'm calling hydrogen my first thing. That's the one that had the first order. That one is, hydrogen is going to be my A. So A is the molarity. And so hydrogen, this right here, this is my A. And then NO, second order with respect to NO, I put that as Y, which means that Y is going to be my B. So the molarity of NO is here. There's my B. And then they also gave me the rate of reaction. And so right here, this is my rate. I'm writing all over the problem, so you can't see the words, but it's okay. The important thing is the pieces that we need. All right, so let's take this equation and just fill the stuff in. So our rate is 3.41 molarity per s, and that's our rate reaction. K is the thing that we're going for. That's the thing that we want, the reaction, the rate constant. And then we have 0.012 molarity for H2, and that one had 1 as its order. And so it gets 1 for its coefficient, for its power. And then the NO is 0.045, and because it had a 2 for its order, it goes there. All right, so let's go ahead and start with those two. So this one is just going to be 0.012 m. This one, when we put it into a calculator, is going to end up with that m squared. And so I realize I probably should have rearranged this first, but that's okay. Yeah, let me do that. Let me go ahead and rearrange this first instead of doing that. So I'm going to go ahead and divide this by 0.012 m to the first power, which will take care of getting rid of it on that side. And then I'm also going to divide it by 0.045 squared. Oh, I forgot to put my m. M squared. All right. And to clean this up a little bit, I'm going to, where are you not erasing? I'm going to move my K over since my fraction bar went a little bit too far there. It's always nice to rearrange things before you get started. That way you don't end up with something that's messier. All right, so my K, I'm going to put all this into my calculator. Everything is just being multiplied and divided, so the significant figures will work out by doing it all. I don't have to do it in pieces like I did with the other problem. I'm not sure where to put my calculator where it's not in the way. All right, so 3.41 divided by, and everything on the bottom is going to be in parentheses, 0.012 times, and I'm going to put this next piece in parentheses, 0.045 to the second. Close that parentheses, close the other parentheses, hit enter. All right, so I need 3 significant figures. No, nope, just kidding. I need 2 significant figures because the 0.012 molarity and the 40.045 molarity, those are 2. So I need 2 significant figures. So if I round it to 1,4 and then the rest zeros into the decimal, that'll take care of it. So 1,4,0,0,0. And let's talk about units for just a minute. This one right here, this M, is like an m squared. So this m cancels, this m cancels, and I'm going to end up with this s is on the bottom of a fraction, so I'm going to move it to the bottom of the fraction down here. And then this m that's left got squared because that square affects everything in parentheses. So I have m squared. So that's my unit. The units might be different for different rate constants because of the different orders changing. All right, let's look at the second problem. In the second problem, here's the reaction I'm given. We're just going to jump right into labeling the things. They want the rate constant, which is K. This is what they want. So let's find our rate and our molarities and our orders. So I'm going to label them out here so it doesn't get too messy. So when in fact, we're going to end up with multiple things. We're going to end up with like a C here because we have 3 products that we're working with. So A is going to be our first product. We're going to call this one A. Keep my brackets around. We're going to call this one B, and we're going to call this one C. So H2O2 is first order, so X is going to be 1, and the molarity of that one is 0.010 m. And then for B, it says it is first order with respect to I minus, so again we have a 1. And the molarity for that one is 0.020 m. And then we have C, because we have a third thing here. And our C is going to be our H2. That one has 0th order. And then it tells us the molarity, 0.00050 m. Okay, when we start putting these in the thing, you're going to notice that I'm going to be raising each of these to the power that the order says. When I raise the C in brackets to the power of 0, anything to the 0th power is just 1. And so this whole section is just going to be times 1. And so we really don't have to put that in. Oh, goodness, let's get rid of that. All right, I'm going to erase this because this is where I'm going to do my work. All right, so for our rate constant, let's put in our rate. We have, oh, yes, let's also include the rate real quick. So rate equals 2.30 times 10 to the 4 m per s. All right, now we're ready. So we have 2.30 times 10 to the 4 m per s equals K times 0.010 m, and that's raised to the first power, times 0.020, also raised to the first power. And this last one, I'm just going to put brackets, put C, it's raised to the 0 power. That means we can just mark that out because it just becomes 1. And anything multiplied by 1 is the same thing, so that doesn't affect it. And in fact, that's what having an order of 0 means. It means that the concentration of that particular part, that reactant, doesn't affect the rate. Yeah, I think that's the only piece I need to pull out from that piece of information. All right, let's go ahead and divide. So I'm going to flip this equation around as I rewrite it. Write K equals, whoops, so I have 2.3 times 10 to the 4 m per s. And these two numbers that were previously being multiplied by K, I'm going to divide both sides by those, so that 2.30 ends up being multiplied by 0.010 m and 0.020 m. They're both raised to the first power, so I did not have to worry about messing with those. Did I change one of my numbers? I think I did. Oh, just kidding. Okay, this was actually supposed to be a 6 in the problem. And somewhere when I typed it, I changed it to a 4. I knew something looked funny there. All right, that should be a 6. Sorry, guys. All right, so K equals, and then let's type this in, 2.3 times 10 to the, is it positive 6 or negative 6? It is negative 6. How did I mess up so much on that one? Can't even tell it's a negative 6. Let's clean that up before we move on. I can't fix the type stuff, but I can fix the stuff that I wrote myself. All right, there we go. 10 to the, let me put this in parentheses, -6. And then we're going to divide that by, and I'm putting these two in parentheses, 0.010 times 0.020. Close parentheses. Alright. Okay, so I got 0.0115, but I didn't talk about significant figures yet. So 2.30 has 3, and then each of the bottom numbers just has 2. The 1 with the 0 that comes after it, and the 2 with the 0 that comes after it. So I'm limited to 2 significant figures. So starting at this 1, I get to keep the 1, and I can round up the second one to a 2. So it'll be 0.012. And on the bottom I have an M from here, and then I also have an S from here. Sometimes it's easier if you want to just write the answer you got and then just know that, you can kind of make a little bubble around it so you can remember that's not right. I just need to get to significant figures. That way you can write it out and decide if you're going to round up or round down, or if there's any rounding at all. Oh, before I stop recording, notice that this one had 1 over m times s, molarity times seconds, and then the one over here had an m squared on the bottom. The units for the rate constant will depend on the overall order of the reaction, because the order of the reaction gives you different exponents. So if you have a squared like you did with this one, you're going to end up squaring that unit too. This one over here had no squaring, so all of our units were just m's. And if you had multiple reactants that all had different orders that were, like even if you had 3 different reactants that mattered and they were all to the first order, you would still end up with 3 m's that got multiplied. So just the units for the rate constant change.